Hello, this is Lab 1 Constant Velocity for Physics 2211, and my name is Lindsay Broadway. So first, just a quick introduction to the purpose of this lab is, since the lab is called Constant Velocity, basically that means that throughout the time of the object's motion, you want it to have the same velocity, so final velocity is equal to initial velocity and all the other velocity values in between. This is essentially a way of practicing Newton's second law, which is that an object in motion stays in motion unless a force acts upon it. So with that part of the forces, there should be no net force, so all forces should cancel each other out. My system includes a water bottle, which is what I use to roll across the meter, and the other surroundings include the table, the air around the water bottle, and my hands to push, and then my partner's hands to stop the water bottle from rolling. So basically, here is a quick video of my experiment. 3, 2, 1, go. Beautiful. Okay, and then I put this data into Tracker. And so you can see I plotted the points of the water bottle to map out a position versus time graph. You can see that in the top right of Tracker. The timestamps from 0 to 4.5 and 7.5 to 8.5, the water bottle was not moving. That was just the time period in between me pushing or my partner stopping the water bottle. So basically, Tracker plots all of these points for you in very small time intervals. So between the time of 6 seconds to 7 seconds, I found the velocity, and the velocity is the change in position, in this case the x position, divided by the change in time. So then after carrying this out, I got about 0.32 meters per second for the velocity of the water bottle. Then I used the standard code that the TAs allowed us to use, and I split it into the time before 4.5 and after 7.5, which is basically not moving yet, moving, and then not moving again. And then also you can see in this section, which is the moving data, I used the slope of 0.32 in meters, which I found from the previous slide. So this is the predicted modeled results. You can see that they match my Tracker data pretty well. There is some differences, though, between the experimental data and the modeled data. So to answer the question of why the data is not the same, it brings into question, was the net force really zero? So in a lot of physics problems, we don't take into account friction or air resistance, and these forces can play a big role in real-world examples, and also the design of the water bottle could have like a bend in it or a dent, so it would not roll perfectly as smooth. So that could account for some of the lapses in the points that weren't exactly overlaid. So then finally, to answer some of the what-if questions, the picture on the left shows you the normal x-y axes, but for example, if you change the axes, then the x value would not change a lot, and the y value would be what you are interested in for the velocity. So you'd look at velocity in the y instead of velocity in the x. And then in the other example on the far right, if you switched both of the axes so that the normal positive direction was the negative direction, everything would be the same, but the water bottle would be moving in the negative direction, so the velocity would then be negative. And finally, my data was very close to the model data. the push must have been strong enough to make the friction and air resistance close to negligible. The three forces that I found to be very present in the X direction were my initial push, friction, and air resistance. And there are other forces working on the water bottle in the Y directions, but they canceled out, and those would be the force of gravity and then the normal force of the table.